Good morning, everybody. It's my favorite day of the week. Welcome to Hackster Café. I'm your host, Alex Glow, and today we have an amazing guest to chat with us, as usual, about hardware. We have Charlie Diaz, who has now become your TARS robot, and the interview that you gave about it has become our most viewed video on YouTube and TikTok, um, which is more of an accomplishment on the Instagram because it's like longer running. But either way, you're just like blowing everything else away. So excited to talk to you about this movie prop that you created that actually walks like TARS. Welcome, Charlie. What's up?
Hi, I'm Charlie Diaz, and I built the TARS thing, and I built a lot of other, little, kind of robotic-y knick-knack things. I got my start with Arduino in middle school, and then throughout high school, I joined a robotics team, and just kind of acquired skills and explored my interest from there.
Yeah, and I didn't mean to cut out your other things that you've built. You are a student at UC Berkeley, and you're creating not just the TARS robot, which is amazing, but also like you've got some self-tying shoes and some underwater ROVs that we're definitely going to dig into. Um, but first, you've got a cool a live demo of this TARS robot. Could you show us
Yeah,
what you've
definitely.
brought here?
So, um, I can turn them on. It'll take a little while to initialize, but here's Tars from the video.
Yeah.
He can walk around by kicking out his torso like this, and then kind of falling over, and then bringing his legs back up and performing that motion a couple of times. He turns kind of the same way that you would turn like a rowboat. So stick one leg forward and then stick one leg back, and then bring them together. And he also has, so this is version 3. For context, there's version 1, version 2, and version 3. Version 2 and 3 are pretty similar, except for the arms. On version 3, I added robotic manipulators that can fold out, and then they have little grippers on the ends, and you can go around and pick up stuff, as long as the stuff that you're picking up is like smaller than a paper clip. So
what have you picked up with it?
yeah, literally paper clips. That's as large as it gets. I was thinking of, because with the here I've gotten an arm that's not attached to a robot. So this is kind of this is kind of like the lower part of a leg, and then there is a standard size servo, which is kind of a arbitrary way of measuring servos, but
Yeah.
you know, yeah, so there's a standard servo here that propels the main arm out, and then the secondary, or the forearm, pops out using an SG90. Now this model is a little bit different. The way that the arms work on the current version 3 is there's a kind of like a direct drive mechanism. So the SG90's servo horn is directly mounted into the forearm, whereas with this one it was a little bit earlier. So you have the SG90 sitting in the main arm, and then you have a linkage system that propels the forearm out. And then inside the forearm, you've got the fingers. Now, the fingers here are kind of flat. I added ridges in the current version 3 fingers, but to help with, like picking up like cylindrical objects, or kind of low profile objects, I guess. You can kind of get under it and pick it up that way. But the amount of torque that the SG90s provide, and the subsequent amount of force that the fingers can impart on an object, is really quite minimal. So thinking about it a little bit more, I've been considering making a version where, instead of having like flat fingers that you use to grip things, kind of hollow out the finger area and then create buckets, essentially, that you can use kind of like a bulldozer,
Like a
construction
scoop.
equipment, to just kind of like scoop stuff up.
Nice. I love talking to people who have just done like an event or whatever, because I can tell that you have your spiel down and you're like, yes, I know
Yeah,
exactly what
yeah.
people are going to ask. That said, what are the other main things that people ask you about with this? I'm
Two
not trying to get
things.
you to do my job for me, but like, yeah.
Yeah. Yeah, the two things that came up the most at Open Sauce, which is the first event that I've actually been to. It was the first, like,
Wow.
kind of maker fair sort of event that I've been to, and also the first one that I've exhibited at. So that was kind of fun. Um, the two most commonly asked questions were, can it spin around like it can in the movie?
Oh, yeah.
And on the if you look up like interstellar Miller's planet or water scene, you'll see like Tars cartwheeling, and
Mm.
can he run that fast? And does he have a humor setting?
Yeah, that's the main one we
Unfortunately,
see on the
yeah.
Instagram.
Unfortunately, we don't have spinning tars, and we don't have humor setting tars yet, but it'd be really cool if the original puppeteer of tars, like Bill Irwin, would like be down to like record a couple of funny quippy lines that you can activate with your tars controller to to make him say that.
That would
But
be
we'll see.
amazing.
Future developments.
I love that idea that, like, in future, if there's a specific thing that goes super popular from a movie, for them to just release things for DIY prop artists and cosplayers and stuff, because that's becoming such a huge thing these days.
Definitely. One of the funny well, I guess is kind of funny issues that I was kind of running into with trying to figure out how to like get tars out there into the like into the wild, get it like into other people's hands, have them like make tars, is kind of similar to actually the R2D2 like builders like group.
Mhm.
The rights to the characters from Interstellar, I'm pretty sure, have not been released by Warner yet, so they own the copyright. So I can't like like sell anything that says here's how to build tars from Interstellar, because I don't have the copyright for that. So I think I'm down to just like building making build guides, which I published one on Hackster.io. So check that out too.
Oh yeah, you should totally check out Charlie's sweet tutorial on Hackster.io, the coolest online community for hardware developers. You mentioned that it might be a little long, but we love that. You got all nerdy with putting the code in there, putting the custom CAD enclosures in there. Love it. And that's exactly the kind of thing that people will need in order to build their own version of the robot. Now, you've shown in this case, I believe this is V1, is that right?
That is V1. Yep.
And that's the metal version. So, what made you choose to go with, you mentioned this in the video, but can you tell us what made you choose to go with plastic instead of metal this time around?
So the evolution of TARS, it actually starts before V1. It was
Hmm.
a Halloween costume that I made in like middle
Oh,
school. I think
yeah.
it was like eighth grade or something. There's actually a picture of it on the article. It started off as like a full scale puppet, basically replicating the puppeteering mechanism that the actual prop builders in the movie used to bring TARS to life. So yeah, there's me walking around with it. It's a little, yeah, made out of, instead of making it out of aluminum and like having a hydraulic lift mechanism, it was me pumping the torso up and down with my, I guess it's my right foot, and then moving it around with my hands manually, and the structure was made out of like wood and foam core board and then spray painted. So it's so it started out as that, and then version one is a little bit later during COVID, when I had to do with my robotics team. We were kind of on a mini hiatus. I was just trying to find something to do. I thought, like, hey, like that TARS costume was pretty fun. I wonder if I could like make it into a real thing. And I fully expected to like not be able to do it, because when you look at TARS in the movie, it's a deceptively simple robot. It's like, oh, there's like 2 or 3 joints at the most, and you can probably get it to walk around that way. It can't be that hard. But then when you think about it for like more than 2 seconds, it's like that robot is impossible to build. So I was fully under the original assumption that there's no way that this can work. So but I figured I'd try anyway, because one of the most valuable lessons you can learn in like building like robotics is just giving it a try, and then seeing how you maybe some of your initial assumptions about how a mechanical system could work are incorrect, and then you have to adjust it, and there's the learning. So I figured at least I would be able to learn something about how walking robots work. But I actually got version 1 to kind of walk. I mean, it definitely walked. It walked 3 steps, and then the 3D printed parts inside of it tore itself apart because it was so heavy and the movement was so sudden and violent, um, slamming down into my desk. And that was partially because of some of the components that I chose. So in version 1, I used nickel metal hydride batteries, I think a total of 16 little cells to power the servos. And for context, nickel metal hydride batteries are like super heavy. And this robot, it felt like a brick when you picked it up.
Mm.
One of the other design choices that I made with version 1 was, well, I wanted it to be um, uh, as faithful as you could. um I wanted it to be like as faithful of a replica to the original TARS as you could, feasibly make. So I figured I'd start with some sort of metal casing. Now, in the movie, they use stainless steel, and I was like, I obviously can't work with stainless steel. I don't have any metalworking tools, so I'll try aluminum because aluminum is a little bit more malleable. And so I started off with aluminum, and I built the case out of aluminum. But the one thing that I learned metalworking was that I don't really like it. It's very difficult to work with large sheets of aluminum when you don't have like a purpose built like metal brake or like a metal bender. Um, and the what you call it, the way that I fastened the whole robot together with a bunch of M3 screws. You can kind of see them in the top and in the front paneling of TARS. And creating so those screws, in order to get the design of a sort of like a flush robot, I used flathead screws. Now, in order to make the holes for flathead screws, I had to not only drill through the aluminum, but then I also had to take like a cone. It was 3D printed. It should have been metal, but you make do with what you have. I used a 3D printed cone that I stuck inside of the hole that I drilled, and then I hammered it down to create kind of like a chamfered,
Like a countersink.
exactly, a countersink. Yeah, sorry, a
No
countersink for
problem.
it. And that was just so much work, and uh, the accuracy I was able to achieve was not like there totally. So I figured with version 2, I'd try to do something a little bit more approachable from my perspective, and also from the perspective of someone who's like has basically no robotics tools, like, or has no like uh, uh, um, their tool set is basically like a 3D printer and a screwdriver, and that's all they have to work with.
Mm.
Um, so
But that means that the tutorial is gonna be, pretty great for people who don't have, access to a metal shop either. That's
yeah,
kind of the
definitely.
beautiful thing about, open source stuff, yeah.
Yeah, definitely. With 3D printing especially, I mean, like, it's just insane, how far 3D printers have come. I started with a kind of a knockoff of a Prusa i3. I started with a monoprice uh, um, FFF printer, and it was okay. It did not have automatic bed leveling. It was like manual bed leveling, borosilicate glass print bed, and like PLA from Amazon, and it was okay. It did the job, but I recently upgraded to like a Prusa Mini, and that printer is just insane. It just keeps going, and there is no servicing that you need to do for it. And yeah, it's an awesome printer, and it's what's enabled me to build things like TARS.
Nice. Oh, yeah, we love hearing about the types of equipment that you use. So, what types of filament do you usually use? Does it depend on the application for, like, heat and durability, or do you have a favorite that you stick with?
The things that I build are not exactly extreme in terms of having to endure temperatures or extreme pressure, or like extreme mechanical situations. So I generally stick with PETG because it's a pretty good balance between, like ABS like strength and durability, and PLA like ease of printing, pretty much. But for smaller applications, like for the arms on TARS, I wanted to kind of try to preserve that flush box like quality of the original TARS. So trying to figure out how to make flush joints was one of the bigger challenges that I had with version 3. What I ended up settling on was actually using TPU filament to create a kind of a flex joint. So when the arm pops out, you can see the main kind of axis of rotation is a flexible TPU printed joint. And the same goes for the joints on the fingers as well.
That's rad. Now, one thing I'd love to go back to, I was planning on asking you what you call this type of locomotion. And did you say you would call it a rowboat motion?
For turning, I'd say it's pretty similar to a rowboat, and honestly, with walking, it's pretty similar to a rowboat as well.
That
Um,
kind of makes sense.
yeah, because like when you're in a rowboat, like if you want to go forward, then you use both oars going in the same direction, and you pull back the same way that with TARS, if you want to go forward, you use both. I guess in this analogy, the oars would be the arms to go forward and then row back. And then if you want to turn, you splay the oars to, turn.
Nice.
And with TARS, you just splay the legs to turn.
Did building the costume help you work out the mechanics for this, or was it pretty different?
It did actually. The way that I build things is I do not have a formal education in robotics or engineering at all. I am a marine science and environmental science major. And most of this I learned in high school. So the way that I understand mechanical systems is kind of intuitive and, like from my own experience, being able to like pilot or operate a thing. So when I was able to operate the TARS costume, I understood a lot better, like the types of motion that I would need to have in order to make a actual, like self-propelled replica, like a viable robot. One of the things I learned was when you watch the behind the scenes of how they made TARS, they talk about a lifting mechanism to lift the legs up and down so that you can create clearance on the ground to move the legs forward and back. Now, when I was 13, I didn't think that this was entirely necessary. So the original costume didn't have that lifting feature in it. It was literally just a hinge and the legs would pivot around it. When I tried to walk in this original design, the what do you call them? The legs would just collide into the ground and you wouldn't be able to swing them forward in order to walk. So I had to take a Dremel and mill through the wood bracings that held the axle to create about like 1 or 2 inches of vertical clearance so that I could move the legs forward and back. Another thing was learning how to turn. So I mean, it seems pretty obvious, the way that you would turn a robot like this is just like, well, you have to move one forward and then kind of like push it back. But that was something that I learned while walking it around. It was kind of like, well, how do you turn this thing? How would you, as TARS, impart force onto the ground to move your body one way or the other? And, it took not too long, but I feel like the hands-on experience of being able to like figure that out from the perspective of TARS was pretty valuable when making the robotic replica.
Cool. So you mentioned that you're studying marine and environmental science, which is awesome, and we'll totally get into that later. But also you started out doing electronics in robotics team, which actually is similar to what I did as well.
Oh, nice.
And do you think that did this affect your decision to get into marine and environmental science, the fact that you were building marine ROVs?
Definitely. Yeah, 100%. The competition that we were part of was the Mate ROV competition. it's a pretty great competition. It's there are like two predominant underwater robotics competitions that I know of. There's the MATE ROV competition, spelled MATE. It's an acronym for Marine Advanced Technology Education. And then there is, yep, that's it. Actually, the team that's in the picture is St. Francis Robotics. They are uh, um, a um, a school that was kind of close to our my team school, Jesuit Robotics. We're both from Sacramento, and they actually
Huh.
won the Ranger section of the international competition that they were at just last year. So actually,
Wow,
just this
cool.
year. So for yeah. Anyway, so the main like distinguishing kind of element between the mate competition and the other competition, RoboSub is autonomous. So you stick the robot in the water, there are no tethers attached to it, and then it'll swim around on its own. With mate, you have a human pilot, which is sort of if RoboSub was the AUV competition, then Mate is kind of closer to modern ROVs in terms of its competition. Because with modern ROVs, you have like a human pilot, and then you have a co-pilot, and then the pilots can like manage the onboard manipulators to like pick up sea slugs or whatever.
Huh?
And with AUVs, it's all autonomous. So on the Mate ROV competition, as a competitor, I was a pilot for my last year as a senior. But before that, I was well, before and during that, I was on the mechanical side of the robot. So I managed things like how do you build the frame. So in this picture, you can see the frame is built out of aluminum extrusion. I think it's 1515 in that picture. And then like what kind of housings do you use? So the main housing in the front, the one with the clear panel, is off the shelf. It's a plastic enclosure rated like IP69 or something like that, which um, isn't exactly the type of rating you would want for like a highly pressurized robot that goes down a couple thousand feet. But for the purposes of a like a student competition where you have to consider like what is a reasonable amount of money to spend on something like this, IP69
Yeah.
is absolutely totally acceptable. So, and then there are a couple of some of the not so obvious skills that I picked up from the ROV competition was how to balance how to balance costs and performance, and also how to determine what types of components you build in house, and then what types of components you build that you don't build, actually, that you just buy off the shelf. So with the housings, it's kind of like a lot of the time that would have been spent in creating a housing could be spent on more um, could be spent on other projects that we want more control over. Like for a housing, what's a housing going to do? It's going to reject water. It's going to prevent water from getting into your electronics. That's pretty easy, and that's not exactly a particularly specialized like thing that we need from what do you call it? Um, that's not something that we necessarily need to control all aspects of.
Mm.
So we can just buy that. But when it comes to something like a gripper, which was also on that was also on that web page, you want to kind of control that a little bit more, because the things that we're doing with grippers are maybe a little bit more specific. So hold on a minute, my AirPods just went out. Okay, here we go. I'm back. Anyway,
All
yeah. So
right.
those grippers, I designed these parallel grippers because of a an issue that you kind of encounter as a pilot when you have when your perspective is from one camera. So when you're looking at something from a single like camera view, you don't have what we have as like humans, two eyes. We don't have depth perception. So when you're swimming forward towards something and you're trying to pick something up with your gripper, if you have like a an angular gripper, or something like a Vex gripper that kind of like pops out and grabs something, it's a little bit more difficult to pilot because you have to take into account how far forward the object that you're trying to grip is, so that when you hit that gripper button, it pops out far enough to grab it. And that's really hard to gauge when you don't have depth perception. With a
Mm.
parallel gripper, you can just line up the object inside the jaws of the gripper and then hit the gripper button, and then you know it's always going to be inside of there. Another thing with angular grippers is when you're underwater, everything is super lubricated. So if you were to try to pick up something like a coffee mug with a angular gripper underwater, the coffee mug is going to be super slippery, and when you kind of come at it with an angular gripper, it's going to push the coffee mug out of your gripper. With an angular gripper, you just go in, close it, and it's always there.
That's so rad. I love hearing about your visual demos are just excellent here. So, you mentioned studying marine and environmental science, and actually, you know what? Let's get into that later because that's more about the future. I would love to hear more about these other things that you've built because there's plenty more stuff that you've gotten into. So, while we're on the ROV subject, let's talk about the Kraken and also
Oh
the
yeah,
vampire
Kraken.
squid. There's two different things, right?
Yeah, vampire squid is I guess what you would call a float, and you see those a lot in marine science data collection, to take measurements like pH and pressure and temperature at different depths in the ocean. And then with a ton of these sensors, with a ton of these floats, you just throw them out all over the ocean, and they broadcast their data wirelessly to a satellite, and then you can collect it all. You can get some really interesting information back about like underwater, like ocean dynamics. Like, is there and like an algae bloom, like in this area, and what are the conditions that could lead to it, and tons of other super interesting information as well. So
It
this
looks
is
so
vampire
epic.
squid. Yeah, it was funny because it is for the Mate ROV competition, but we were given like what would you say? Uh, I pretty much just built that one in my room as like a senior project, just because I thought it was kind of fun. And so uh, I just thought, let's try to make the float for the competition, but let's also just make something that looks really cool. So like there's some obvious, like color coordination with the reds and the blacks and the different tones. And then you have to make it out of clear acrylic because you have to see all the cool electronics on the inside.
Of
So
course.
exactly. So what we've
It
got
kind of
going
reminds
on.
me in design of like a Dyson where it looks very functional but also like quite pretty.
Yeah, thank you.
Anyway.
So so the way that floats work are that vampire squid would actually move through the ocean pretty much the same way that you were like looking at it. It goes just straight up and straight down. So it starts at the surface of the ocean, and then it gets a cue from like the satellite that you have to go down and dive. So what it'll do is it'll use a buoyancy engine, which basically shunts out oil from an internal bladder into an external bladder, which, well, actually, no, it would shunt oil from an external bladder into the internal bladder, which would decrease its buoyancy and then send it down to the bottom of the ocean. And when it wants to go up, it would reverse the process, and then it would go straight back up. And that's how it can move through the ocean. And then while it's moving through the ocean, it'll stop at certain depths that scientists deem, particularly interesting for their studies, and then it'll take measurements as it goes down.
Could we dive into that, oh, as it were, just for a second? Because I've always actually wondered about this. Is it controlling the buoyancy because you're compressing the air inside of it? Like, it's all the same stuff
So
inside the robot. How does it?
that's kind of funny. The way that vampire squid works, and it's not exactly the same method as kind of more commercial floats like the Go BGC float. The way that vampire squid works is there is no oil system. It is all either air or it is water. So at the bottom of vampire squid, you'll see there's kind of a syringe sort of sticking out of the bottom. So what that does is it draws in water, and when you draw in water, you decrease the volume of air, since the volume is now being occupied by a denser material the weight that's kind of applied to the object of the float itself increases, so the buoyancy is overpowered and the thing just sinks. It's the same method actually as like a modern submarine. So it's got a ballast system.
Mm.
So yeah, so up there actually at the top, we can kind of go through it. So this is the
Sure.
battery box. It's got a cork at the bottom in case the batteries like explode, and you don't want a pressurized container underwater where there are humans. So if the batteries explode, instead of creating a pipe bomb, literally, it will eject that black cork at the bottom, and it'll be able to vent. It's not perfect, but it's safer. So below that, power gets passed with two or three. Okay, I forget what the third wire is. Anyway, power passes through cable assembly into the main like hull of the vampire squid. Also, a note on the name vampire squid. Um, I just named it vampire squid because it was red. And vampire squids are red, and they also go down super deep.
It's also got like
So
a syringe at the bottom, which is a little bit like a
oh yeah,
like
exactly. Yeah, that's totally that was absolutely intentional. Anyway, so power goes through the power cable into the main housing where it is controlled by where the power goes. Oh, I remember what the third wire is for. One of them goes to an Arduino Nano, and then one of them goes to a DC motor driver. So the
Mm.
Arduino Nano runs on a timer, and that's how you get you're controlled up and down and up and down. Again, not a perfect analogy to modern, like floats because they are controlled wirelessly, which was a task that they added later to the composition. But this one is controlled with a timer. Now, when the Arduino says go down, it'll send, I'm pretty sure it's communicating over I2C to the motor driver. It'll tell the motor driver to, like turn on. And so what will happen is the motor driver will activate the onboard DC motor, which drives literally this is the parts I used were spare parts for like an Ender 3, I think. So it's the y-axis of a 3D printer right there. So the DC motor will drive a really long screw that is attached to a nut, that brass item there, which is attached to that red assembly is all the plunger of the syringe at the bottom. So
Uh-huh.
when the plunger goes down, you increase the volume that's occupied by a lesser dense material, air, and then when the syringe pulls up, that volume gets occupied by a denser material, water, and then that's why you would sink.
Mhm. Excellent. So this is really cool, and thank you for telling us about the name. And then B, also, I wish I could spend a million years talking about all of this, but let's move on to the Kraken because we've only got an hour. Maybe we'll bring you back on when you have another cool thing, but we'll get into that later. So tell us about
Totally.
this guy.
Absolutely. So this was kind of uh, a thought experiment I had kind of late last academic year, so around like April or May. I was thinking, what is so when you're building an ROV, ROVs are expensive. No matter what bracket, what type of ROV, whether you're making a commercial one that's the size of an F-150, or you're making an amateur one for a student robotics team like the Jesuit Robotics Nautilus. So when you're making an ROV, what is the most expensive component? There are computers, there are waterproof housings, there are frame materials, but possibly the most expensive and the most frequently used item is a thruster. So you've got Blue Robotics T100, T200 thrusters, which run you from anywhere from like $150 to $200, and then with ROVs that use like a 6 or 8 thruster configuration, you have to have 6 or 8 thrusters, which turns $200 into like yeah. So I didn't do a whole lot of math in school. I think $12,000 or $1,200, $1,200, something like that, $1,200, which is a ton of money to drop on, like just kind of a fun little project. So the goal with Kraken was to create a monothruster ROV that uses thrust vectoring to move to direct the thrust from one thruster to enable movement in multiple axes. So I've actually got Kraken here. So this is it. Let me scoot back my chair a little bit. So this is Kraken. The one thruster that I have is down here and it's fixed. It's shooting straight back. When you move kind of back a little bit further, you see this assembly here is a kind of a thrust diverter. You can't see the like the flipper mechanism exactly, but yeah, here. There's a panel that shifts, that angles up or down and sends the thrust from the vector either straight out the back or into these dual tubes. Now these tubes move the water up through into these kind of thrust vanes here in order to shoot the water, which would allow you to like turn the ROV. So these thrust vanes are driven by MG90 servos inside the main hull of the ROV. An interesting thing about the main hull of the ROV is that it's printed out of resin. So instead of having to take like a bunch of FDM prints and fusing them together with epoxy and then painting it with like refrigerator sealant or like some other spray epoxy with multiple coats and then sanding it down and then spraying it and then sanding it and spraying it, only to find that there was a minor like small little crack that you didn't get, and now your whole thing is flooded and your electronics are gone. With SLA, you can just print the thing the way it is. It's pretty waterproof, and pretty is a general term. I've only been able to test this in like a 15-foot pool, but I did forget it overnight. So endurance testing, right? 24 hours,
Nice.
and no water ingress. So another fun little thing that I made was the waterproof bulkhead on the back. It's actually fully 3D printed. So kind of getting back to the main design philosophy of the ROV is that you wanted a monothruster ROV. So when you're using only one thruster, you have to find a way to move that thrust, either like to make it go forward or to make it go backward or to make it turn or to make it go up or down. So how do you do that? With the two thrust vector vanes on the side, which are magnetically coupled to servos on the inside, so there's a waterproof barrier between like outside and inside. You can rotate like one forward and one backward like this and get kind of a you can't really see the difference there. Here, this is a little bit better. So you can rotate one forward and one backward like this, and then you can get kind of an effect that causes the ROV to twist this way, or you can do the opposite to make it twist that way, or you can have them both point in the same direction to make them go forward or to make them go backward. And then if you point both of them straight down, you can get the ROV to go straight up. And then if you build your ROV so that it is negatively buoyant, which is it'll sink in the water instead of float or just kind of sit there, then if you just turn off the thruster, then the thing will drift down. Now, as I progressed with the design of the Kraken, I started adding all of these things like, oh, let's print it out of SLA and let's use, like some really, like cheap electronics, which turned out to not actually be so cheap. And all these things. So it really turned into like a personal kind of technology demonstrator. How far can we push the skills that we already have? So the thing that I was kind of most surprised and most like proud of actually was the waterproof bulkhead here. It's both parts, so the bulkhead itself and then the plate that you screw onto it are printed out of resin, and then the seal in between it, the gasket, is printed out of TPU as well. And then you use silicone grease to kind of make the seal make the contact a little bit better when you screw it all down.
That's so cool. We have a comment from Taylor who says he should start a YouTube channel. I'd watch more of his projects. Have you thought
I
about doing a
definitely
YouTube
should.
channel?
I've thought about it a little bit, but I haven't really. I didn't really think that I had a whole lot of interesting things to post about. So it's nice hearing Taylor say that I've got some interesting things to post on a YouTube channel.
Well, hopefully you do, because you know, as we saw with your video just going super blowing up on our channels, you had to create a new TikTok account in order to sort of capture that interest. And so, folks, you know, he created his tag after we had published the video, which meant we weren't able to tag him immediately, which means that you currently only have 20 followers, but there's so much interest in this. Please go and follow Charlie on TikTok, because this is where, well, this is partly where you've also already been publishing a bunch of stuff on Instagram.
I've got a larger backlog on Instagram, definitely.
So go follow Charlie if you want to see more of his stuff, and maybe if you start a YouTube channel somewhere down the line, people can learn about it there. But like, if you want to go follow, like, there's so much agreement. Everyone wants to see more of your stuff. No pressure, but everyone, that's where you can go follow, and we've got these links in the description as well. Be sure to follow Charlie, because he's got so much cool stuff going on. We've still got a little bit of time, which is great, because I'd love to ask you about some more stuff. Let's see. So in your TARS video, you mentioned, and also in this interview, you've mentioned how the first thing that it did when you built it out of metal was sort of tear itself apart. And I'm curious, in this and your other projects, what tends to break first? And how have you sort of upgraded your durability there? You were talking about this waterproof bulkhead you built that's really good for like keeping the water out, which obviously with ROVs would be a point of failure, but also it worked the first time, so that's cool.
That was kind of unexpected, yeah.
So what other have there been any fun catastrophic failures?
Fun catastrophic failures.
No vampire squid explosions, that's cool.
Is it when you say fun catastrophic explosions, do you mean like due to an issue with the design or due to an issue with operation? Because
I guess either way.
They're kind of both. So in terms of design, definitely the suspension of or the lack of suspension on TARS version 1. So with TARS version 1, I think there might be a picture of it on the website that I sent you. There's kind of if you look on the inside of it, it's all printed with polycarbonate, and there is no, scroll down a little bit.
Ooh.
A little bit more, I think. Oh, no, I guess that's it. All right, so the one on the left, behind the screen is where the main, like, like pumping up and down action is for the legs and for the torso. So when you take a step, all that mass needs to stop. And when it stops, all that energy is imparted to the TARS system. So all that energy is absorbed by the 3D prints generally. And the issue with 3D prints absorbing shock is, especially with polycarbonate, as I found, it's really not that great at it. And so you'd have things like the bearings on the sides here ripping off, or you'd have one of the interesting issues that I had was I built I redesigned the internal like 3D parts of the robot so that the 3D prints would not fail. Like I beefed them up way more than they needed to be. And what ended up happening was the 3D prints wouldn't break. The aluminum servo horns that held the servos onto the legs would start stripping. The aluminum would start just peeling off. So that was a really interesting and fun issue to work through. Sadly, I kind of just abandoned that design because it was just so much of a pain to work with. But as I moved on to version 2, here I've got this is version 2. as I moved on to version 2, I took some of the learnings from version 1, namely, it needs a way to absorb all that shock, and I applied it to the design. So here, when TARS takes a step forward and all that shock enters the main drive system. Okay, so first, one of the things that I did was I replaced some of the 3D printed parts with aluminum. So this aluminum bar here, it didn't exist in the first version, but like this is one of the things that I decided there needs to be more metal on the inside. So when the robot takes a step, all that shock, instead of going into the 3D prints, goes into a spring system here. I don't know if you can really see it that well, but here you go. So you can kind of see springs there.
Oh,
So when it takes a step, some of the shock goes into the spring, the suspension system, and the springs absorb it instead of the prints. So that was one of the big things. Yeah. In terms of human catastrophic failure, well, actually, okay, so let's talk about more design catastrophic failure with Kraken specifically. So the way that I designed the thrust vectoring system for this robot was based on like an F-35 or an AV-8 Harrier jet, where the underlying assumption is that with those designs, with the engineers who designed those machines, that the medium that would be passing through all of these like channels is air and not water, which, I mean, they're both fluids, but one of them is compressible and one of them is not. So that's kind of important to note with some of the failures that happened here. So first of all, the thruster that I chose was underpowered. When you send the thrust from this thruster back into the thrust vectoring, like channels and whatever, and then it comes out the other end through the vanes, there simply is not enough thrust to accomplish tasks like rotating or like moving up or moving down. It pretty much just sat in the water, and you could tell that it was trying to do some things, but it wasn't really working all that well. Another issue was in the design, I used magnetic couples to create a way of passing or conveying torque through a solid face. So with conventional motors, when you're trying to waterproof them, you put something called a shaft seal, which is basically just a fancy gasket on the output axle, and that bridges the gap between the output axle and like the rest of the housing. So you can create a waterproof seal that way. But when you're like me and you don't have access to super great machine shop tools, creating a like a housing to use a shaft seal with that level of tolerance, with an acceptable level of tolerance to prevent things like gaps forming between the shaft seal and the axle, it's really difficult to do. So what I came up with was applying magnetic couples to servos. So the servo horns, instead of directly contacting surfaces like the thrust vector vanes, the servo horns are attached to magnets, and then on the opposite side, and then these servo horn magnets are pressed up against a clear wall like this, and then on the other side, you have an opposing set of magnets that are attached to the thing that you actually want to move around, like the thrust vector vanes.
yes.
Kind of similar to if you ever played with a pair of magnets on a table, and you have like one underneath the table and then one above the table, and then like you pull your sibling over and say, hey, look, the magnet's moving around on its own, and it's really you with the other magnet underneath the table dragging it around. It's the exact same idea.
Do you have siblings?
I do. I have 3 siblings, and they're all great. They're all awesome.
Shout out
One
to
of them's
Charlie's
going to college
siblings.
right now. Yeah, Charlie's siblings. Shout out, Gracie, Sophie, and Henry. You're on the internet now.
Oh yeah.
Anyway, so one of the issues that I had with the magnetic couples was that they simply weren't able to provide enough torque. So sometimes you'd end up with situations where the vane would be here, but the servo would be trying to get the thing to be here, but the couple between the servos would just break, and so it would just get stuck in one position. And then another thing was, when I put this robot in the water, this tape didn't used to be, all over here. It used to be glued together. But when I put it in the water, these tubes were full of air, and if you drop it in the water, then these tubes want to go straight up, and the rest of the body wants to go straight down. So they both go the directions that they want to go, and the rest of the body kind of leaves the tubes floating around. And so, that was one of the issues. So thinking back on the mono thruster ROV design, I'd kind of like to, instead of having a stationary thruster that sends its thrust into vanes, and then that's how you control the direction of the thrust, I'd like to have kind of a mobile thruster that you can move around and you can gimbal independently, and then kind of like a lawn dart behind that, and then you'd be able to point the thruster in a direction and then turn it on, and then it'll kind of drag the lawn dart behind it, and then you'd be able to swim around that way. But well, we'll see how that goes in the future.
We have a request from James about flooding another story, but we've only got a few minutes left, so I feel like maybe we'll save this for next time. But thanks for chiming in. Your friends are here to support you with tales of glorious failure. We'll definitely have to ask you about that another time. For now, I want to make sure that we get to these self-tying shoes of yours, because this is a sort of switching gears kind of situation.
All right.
You're not just about ROVs and robots. You also have made the the Back to the Future dream self-tying shoes.
Self-tying shoes. So I guess the name self-tying shoes is a bit of a misnomer, as it says on the screen, but because there aren't any laces to tie, it's instead kind of like a buckle mechanism. So in the picture, you can kind of see, I don't know if you can point out the servo that you see there. Yeah, so the servo drives a aluminum servo horn that is attached to a buckle that goes straight across to the other end of the shoe. Now, in order to tighten the shoe, you get the servo to rotate the servo horn about 180 degrees, and then that pulls that whole buckle down over the tongue of the shoe. Now, one of the issues with servos is they're super power hungry because they're DC motors, and they're constantly on trying to maintain position. So what I came up with was drilling, well, not necessarily drilling, it was printed this way, but there's a hole in the plastic that I attached onto the servo horn that fits a, lower down, you can see kind of like a red block with wires coming out of it. So that's a solenoid, and when you turn it on, it fires a pin. So when the servo is in its 180 position and it's closed over the tongue, the solenoid fires a pin into the servo horn, and then you can turn the servo off. That releases the servo horn just a little bit, so you create a little bit of pressure between the servo and the solenoid pin. And then at that point, you can turn the solenoid off as well, and the whole thing will hold position, and it'll hold it pretty well. You can, jump around and it won't unhinge itself. So that way you can turn off both the servo and the solenoid, the two most energy intensive components of this design. Now, the whole thing is controlled with an Arduino Nano. And in order to initialize the latching or the unlatching process, you have an Hall effect sensor, which is essentially a magnet sensor attached to the heel of each shoe, and then you have magnets in the toes. So when you bring your heel to your toe, it initializes a process that it initializes the latching process, or if it's already latched, then it initializes the unlatching process. And with a LiPo battery, you can get the Arduino Nano to run pretty much all day long.
Is this a custom PCB you made? The auto shoes?
Mm-hmm.
Look at that!
Yeah. It started out as a prototype on a breadboard, and then I worked it down onto a manually assembled shoot, what do you call them? Perf board, just to prototype the layout. And once I was relatively happy with the layout, I designed a draft in EagleCAD, and then I had that sent off for manufacture. And then it came back, and then I realized that a lot of the components, a lot of the surface mount components, were really small and annoying and difficult to assemble. But I assembled them anyway, and I have not yet revisited the design, but it actually works. I forgot where I put it because I just moved, but I'll be sure to post an article or a video about that on Hackster.io later.
Yeah. And was this the first PCB that you designed, or?
It was actually, yeah, yeah. This
Nice.
was the first PCB that I designed. It's a pretty simple breakout board for an Arduino Nano. There's no like microcontrollers soldered directly onto it, but I'm pretty proud of it.
Yeah, how did you learn about this? Did you use any templates?
Well, one of the great things about being on a robotics team is that you've got people with diverse experience in different fields, all working together. So if you want to make something and you want to learn how to make something, you can just ask someone. So I asked one of the electronics team members, Jonah Reynolds, about like how you like even like get started, like how thick do the leads need to be based on how much current you're passing through it, and so
Nice.
I consulted him and a couple other members, and obviously, like YouTube and online, just to like learn the basics. And then I was able to make this, and yeah, it was a first step into PCB manufacturing.
Oh yeah. Did you use KiCad, EagleCAD?
I used EagleCAD. Yeah,
Nice.
we're kind of in the Autodesk family, I guess. I use
Fusion
Fusion
360 and
360,
stuff.
and yeah.
Sweet. Okay, well, we're coming to the end of our chat here, sadly, but can't wait to see more of your stuff. As mentioned below in the description, you can find Charlie on Instagram. Be sure to go follow his new TikTok. You can follow him on Hackster, and also keep up with his adventures at charliebdiaz.com. I feel like I had well, okay, yeah, tell us about your future. Now we get to ask about this. Okay, so you're studying marine and environmental science at UC Berkeley, is that right?
Yep.
And you've built ROVs, you're into robotics. What are your plans for the future? Are you already employed? Are you thinking about a certain type of profession you might want to go into? Are you going to keep going with the robotics, with the marine stuff? What's it look like for you?
I am currently unemployed. Obviously, I'm well, I guess not obviously, but I'm a student. I'm looking for research positions this semester. I've got a couple that I'm currently applying to, biogeochemical labs and climate science labs. In the future, I'd like to find a profession that allows me to kind of combine my interest in robotics and my kind of obsession with like figuring out mechanical systems with my passion for preserving the environment, and that could look like creating actual like commercial floats to go out and like take measurements in the ocean. It could be creating sensor platforms on the ground that like just take measurements from the atmosphere, and you can track like climate change with that. Or it could even be like aerial based flying drones that like take scans of forests to determine like regrowth or decay in certain areas of wildland. Anyway, another thing that I also find kind of interesting is firefighting. I feel like there's a lot of area within firefighting that you could potentially apply robotics, though I'm obviously not an expert in that. But I think that could be an interesting career as well.
Oh my gosh, there's so much that we could dig into there. You mentioned earlier BGC floats, and I looked those up, and it turns out that that stands for biogeochemical floats. So you're interested in this kind of thing.
Yep.
And then also, I gotta mention that we've talked a bunch previously with people from So Far Ocean who are doing sort of the type of thing that you're talking about with like
Nice.
sensor floats. I would love to connect you with some of them if you're interested. And also, for everyone who's watching, and also maybe you, everyone can feel free to check out a previous contest that we did with NXP, where it was focused on, this is sort of an annual challenge we do with them actually at this point. Each time there's a different challenge. The first one was fighting fire with drones, and in general drone technology, and now we've got more land ROVs and stuff, doing stuff with agriculture, all kinds of stuff going on. But yeah, be sure to follow us for more interesting stuff around contests. I love what you're doing. I think it's so cool, this concept of blending your passion for like technological passions and what you like to build with the drive to create a better future for everyone and for the earth. That's absolutely inspiring to me, and I was over here like silently cheering. Love what you're doing, and thanks so much for sharing your robots with us. This has been just delightful.
Absolutely. Thanks for having me.
Yeah, and thank you everyone for joining us. Have an awesome rest of your week and hack on.